recorded.
All right. Welcome back. We'll join in a couple of minutes. We'll restart.
Good afternoon, everybody.
Good afternoon.
Sir, am I audible to you?
Yep, I can hear you.
Okay, sir. So we can resume our session.
Okay. You'll have to give me sharing rights again.
Yes, sir. Sure. Given to you.
All right. So coming back to our demonstration, we took a look at some of the model classes like the blockchain, the block, and the transaction. And we were going over the process of starting the blockchain. Now, at the very outset, when we call the constructor of the blockchain, what we basically end up doing is first we initialize the blockchain with a difficulty level and an empty list of blocks. And then we initialize, we create a block and calculate its hash and keep it inside the block. Then we call a function called mine block, passing in the difficulty level that we've assigned to the blockchain. Now we'll shortly look at what this mine block does. Once it's mined, then we add this block B that we've created to the list of blocks in the blockchain. So this is the whole initialization part where we have the constructor of the block, which is accepting some basic fields, and then creating the first block. The process of creating the first block is these two lines. And then once the first block is created, it gets added to the list of blocks that we have made as a part of the blockchain. Now let's take a look at what mine block does. And remember, mining is the process in which we identify a hash which has a certain difficulty level. And that difficulty level is passed as a parameter. So remember that difficulty level is the number of preceding zeros. Now, mine block is a part of the block class itself, which means it's going to operate on the object of this class. The first thing that mine block does is it initializes the nonce with 0. Now, obviously, our intention is to keep changing this nonce and calculating the hash until we reach the hash which has the right level of difficulty. To be able to do that, the first thing that we initialize is a string with a certain number of zeros preceding it, which could be a string like this, which has 5 zeros, or a string like this, which has 6 zeros. And once this string is initialized, we create a loop. In this loop, what we do is first we calculate the hash of the block using this get hash function. So if we take a look at this get hash function, it just returns the hash that was pre-calculated. And then it checks whether it starts with this string or not, or this string, depending on how many zeros we have. So let's say if this is the hash that's been identified, if it has like 5 zeros, then this loop is completed. Now, till the time the hash that we are calculating actually satisfies this condition, this loop will go on. And what this loop will do is first it will increment the nodes. Then it will calculate the hash using that same calculate hash static method. And then it will print it out or log it. So this while loop, it will be executed a random number of times, but that random number of times is going to be proportional to the level of difficulty. The more the number of zeros we need in the hash calculated, the longer will this loop run. And in this loop, we basically represented the mining that forms the part of proof of work consensus. So once this mine block completes, we will have the right hash in place, which is going to have the right number of zeros. And our first block will be basically added to the blockchain. So this is the process of adding the first block, which is something that we're doing in the constructor of the blockchain. Now we go back to our start chain logic. We've called the constructor with the difficulty. We've got the first block. We've got the blockchain setup. Now what about the rest of the blocks? Are we going to add more blocks? Yes. So first thing we do is we'll create a list of 4 transactions. This transaction will have, these 4 transactions will have some hard-coded data. So what we are doing in that create transaction static is that we are passing the number 4, which basically tells this method call that just create 4 transactions for us, and then return it to us as a list. This is a list of 4 transactions. Now the thing to remember is that in the real world, it will not be created in this way. It will be submitted by the users. We are just doing this because we want to test our blockchain and we don't have a way in which we can have users enter transactions. We can do it, but then this will become a very complicated project. For demonstration purposes, what we've done is we've created a set of 4 transactions. Now, and you can follow these comments when you're checking out this code to be able to ascertain what is happening. First, we create a few transactions. Then we add them to the block. Which block? Just a block that we'll create again in the same way. So we've got this blockchain initialized. In this blockchain, we have a function called new block, which accepts a list of transactions. Now, let us see what this new block does. What this new block does is, number one, it accepts this list of transactions, and then it creates an instance of the latest block. So this new block will basically operate on top of the latest block that is there on the stack, which at this stage is going to be the genesis or the first block that we created in the constructor. So let's see how it gets the latest block. So it's very simple. It goes back to the list of blocks that's there in the blockchain, and then just retrieves the size of that list and gets the top one by sub. So since the list starts from 0, so the size of the list, if it is 4, then the latest block would be third. If the size is 3, then the latest block will be 2, because it starts from 0. So 0, 1, 2. So this is the latest block. It retrieves this latest block. And once this latest block is available, the objective is that it needs to pass, number one, the right index of the block, which will be the latest block index plus 1, because we are adding 1 on top of the latest block. Then we are entering the current timestamp, the latest block's hash.
કારણ આવા બધા કેસ થાય ને કે પાછળથી એવું
પ્રોગ્રામિંગ
અમવું પડે કે તમારું કામ આપ્યું જ નથી, આપે બધું થયેલું જ છે, સફર થયું જ નથી.
Sir, sorry for the interrupt.
No problem. So this block constructor, it's accepting the index of the block, the current timestamp, and the hash of the previous block, which is the latest block, because we are creating a new block. So we need the hash of the previous block, which had been calculated when the block was getting created. So we have the hash here. And then we enter the list of transactions that need to be a part of this block. So if you look at this constructor, it's doing very similar to what we did when we were setting up the first block or genesis block, except that now it has a list of transactions. It also has a previous block, and obviously it assigns all of these to the right field values. Then it has a list of transactions in which it adds all the new transactions that are being added. Ultimately, this list would have, since it's a new block, this list would be empty. This add all function adds all of these transactions to that empty list. So it becomes like a complete list. Then the nonce is initialized with 0. If you're creating a new block, you don't really need this statement, but it highlights an important point. And then finally, we are calculating the hash of this block. So we've seen how this line of code works in our Genesis block or first block discussion. So we've created a list of 4 transactions. We've added it to a new block that we generated. Then we add this block to the blockchain. So we created an independent block. It's not a part of the blockchain yet. This add block function, what it does is something very simple. First, it checks whether, although this is not very necessary, we just check whether it's null or not. If it is not null, then it checks, then it just basically mines the block, which is calculating that right hash with the number of zeros. And then after mining, it adds the block. So every time you add a block to the blockchain, you'll have to do some mining. So this mining is important because the current hash that you have, it needs to be updated with 000 and the right knowns. So you've added another block to the blockchain. Once added, you just print out the block number and everything. And you do this again. Same process. This time you're adding just 2 transactions, but those 2 transactions basically get added to this variable called block2. And then you add that block and just print it out. So we added 2 blocks. This is the 3rd block. And then finally, the 4th block. Now, the thing to understand about this is that the objective here is to replicate what happens in the real blockchain, which is why you can consider this to be actually a test case. When you be running the blockchain, these blocks and all the transactions, they'll be created by either a scheduler that's constantly going to look for transaction size or transaction count. And once, let's say, a set number of transactions are received, then it runs this logic. Add those transactions to the block, add the block to the blockchain, which internally mines the block also. So we've added 4 blocks. So far, so good. Now, if we are one node, then so we have this entire blockchain in memory right now. We're not saving it to a file or a database. So we don't have the ledger yet. We have a ledger, but it's inside the memory. It's not on disk. There's no database in context or in discussion. So what we have to do is, let's assume that we are also the node that does the verification, which means that we have to check that the blockchain that we have created with 4 blocks, is it a valid blockchain? And this is that consensus part of things. So we have implemented a function or a method inside the blockchain. This is a core of the consensus. Let's check what it does. It returns a Boolean, which will be yes or no, which will say whether the blockchain is valid or not. The first thing that it does is it calls a function called is first block valid? And that will return either true or false, depending on, if not really return true, because if it's true, then it will proceed to the next set of blocks. But if the first block itself is not valid, it will return false and stop the process. So let's see what it does to check the first block. So and the problem with first block is that it has to be validated in a different way because it is the first block. There's no previous block hash. So the first thing it does is it gets the first block from the list of blocks by, getting the 0th element there. Now, first it checks whether the index inside the block is actually 0. If it is not, then it will return false and the process will stop. Now, it's obvious that this check is important because what we're trying to do is to ensure that it is actually the first block. So first thing we check is the index. Second, we ensure that the previous hash should be null. If it is not null, return false again. All good till here. Then we check that if the calculated hash of the first block equals the first block hash itself, or not equals, then return false. And if it is equals, then we're basically good. So the first line is it's checking whether the first block's hash is null. And if it is null, then check. If it is not null, then check whether the calculated hash is equal to the right hash or not. So these are the steps for validating the first block. Once we've checked that, then we have obviously the rest of the blockchain to also verify whether the rest of the blocks are good or not. So we are in this function call where our intent is to check the entire blockchain. And we pass this step. Our first block is valid. Now we have to loop through the rest of the blockchain. So we start with 1 because 0th block is already done. And we'll continue till the size of the block is reached. This is a for loop. Everyone's familiar with loops. And then we get the current block and the previous block. For our verification purpose, we need both of them. And then we've implemented a routine called is valid new block, which means is the current block a valid new block or not. And let's see what this processing is. So we've implemented is valid new block. It accepts the new block and the previous block. First thing is checking is that both of them should not be null. The second thing it's checking is that the index of the new block is just one level before the index of the previous block, which means if index of previous block plus 1 is not equal to the index of the current block, then there's a problem, return false. So all of these steps and every verification that we're doing is a process of consensus. Then we have a hash matching process. First we check is the hash of the new block null. Let's say if it is not null, we've calculated it. Then we check if the new block's previous hash field, if it is not equal to the actual hash of the previous block, then there's a problem, return false. So this is that critical new block to previous block hash comparison. Then we check whether the new block's hash, and it's being recalculated here, is actually equal to the hash field value that we stored when we added the block, which means that after the block was added, no one changed the hash of the block. If that equality is not there, then return false, else return true. And obviously, if these nulls fail, then you have to return false too. So that is the second validation that we perform, which validates two blocks at one time, the current block and the previous block, the current block and the previous block, looping through the entire blockchain. So this is our logic. This whole process in the real world, when you have an actual blockchain, it's done automatically. We don't have to run it. It's sequenced in such a way that it gets executed repeatedly. So now what we'll try to do is number one, we are going to set a difficulty level of 4. And then we will try to run this blockchain. So most of what happens is available on this console to view. Now remember, the difficulty level is 4 and the objective is threefold. First, add the first block, which is very easy and simple to do. Second, add 4 more blocks after mining them. Third is to verify the blockchain. Now let's see what did we do. Okay, I cannot show you the entire console. I'll have to run it again because there was a preference that limited the output. So as you can see, although my difficulty level is really small, 4, but it still takes good amount of time, and the number of nonces that I'm calculating are in the tune of tens of thousands. Now let's go back to the start. The first thing that we print is start chain. So what start chain does is basically indicate that we've started the process here. This is starting chain. Then it creates the blockchain and does its bit. Now this repeated outputs that we're getting is for nonce calculation as each block is getting added. So if we scroll through this, let's see how much time it takes for the second block to get added. By time, I mean the number of nonces that it had to calculate. So it's at 16,000, 27,000. And somewhere here it found the block. Let's scroll back. As you can see, the numbers have become small because this is the next block being calculated. I'm just having to scroll through. Yeah, it's right here. So this is where it found the right nonce after 1,40,000 executions. So you can see that this nonce, it has 4 zeros. 1, 2, 3, 4. Not really nonce, the hash. It has 4 zeros, which means it satisfies the difficulty condition. The block was added here, and then it started the process for the next block. If you want to follow through with that, let's see how many nonce it needed to calculate for this iteration. It's a bit tedious to do. Anyway, I just have to get better at scrolling to. I just need to get better at scrolling to reach that number. Yeah, it's closed now. So now it was a little less, 73,000 instead of 140,000. But the thing to notice is that now we've got a hash with 4 preceding zeros. So something similar was done till we got to the 4th block, found block 4 hash, blah, blah, blah. And then we did the verification. Now the verification was really, really fast. As we had stated earlier, we need a verification process to be quick. We validated the 0th block. We validated the first block, second block, third block, and fourth block. So you can see the hashes were all with 4 preceding zeros. Now what I will do is I will increase the difficulty level by just 1. And I'm going to re-execute this code. Meanwhile, and it's going to take a good amount of time to actually complete. What I wanted to understand is, are there any questions or thoughts on what we did in this demonstration? So after this run, we will jump to Ethereum and we will do some hands-on work. We'll not go through slides. And this will be a precursor to what we want to do tomorrow, a part of which will be resumption of our Ethereum exercise, and then another part would be Hyperledger. So you can see it's still continuing, although the increase in difficulty level is just 1, but I don't think it's even found 1 block yet. And I can feel that my system is getting heated up. So any questions, thoughts, comments on what we did? We basically are going to wrap up the agenda for today with this, and we are borrowing some time or we borrowing some part of what we want to do from tomorrow's agenda to get a head start.
Okay, sir.
All right, so let's just wait for this to complete, and I don't know if it will. Okay, there was. So, I mean, my machine was not able to process it. There is an out of memory, as you can see, primarily because I've asked it to do too much. So basically trying to mine at a, difficulty level that is too difficult for this machine. So I'll have to pause this. On a good day, it actually executes with 5 or even sometimes at 6. So with that, what let's do is let's first summarize what we've been successfully able to achieve. We were able to understand how consensus works, and we were able to see it working through our proof of work demonstration, where different types of verifications are being done before a block is committed to the blockchain. Having said that, our next objective is, let me close this. So this is an Eclipse environment in which, which is a very popular environment for Java development. Now, having completed this, what we want to do is now jump to an actual framework, Ethereum, which is a very popular platform for smart contract development. And we've done a part of this already, in which we were able to see a transfer transaction happening, where I showed you yesterday that I have a wallet in which there are some ethers, and then I did a transaction you could see on testnet. Now I'm going to talk about something similar, but our transactions are going to be contract transactions. And the first thing that we need to understand is a little bit of Solidity to familiarize ourselves with the Solidity development environment. And the easiest way to start off on Solidity is to go to this URL, remix.ethereum.org. What it loads for you is an integrated development environment that is like an in-browser application. So you don't have to install anything, you don't have to download anything, you don't have to set up anything. It will automatically create this environment view for you, from where you can do your smart contract development. It also allows you to do your smart contract deployment and some amount of testing. And this is all compatible with the Ethereum blockchain. So when you load this, what you see is this like split window experience, in which there is this left side which has a list of files, and then there is this top right corner which has which basically shows you the contents of these files. And then at the right hand bottom, you have what is similar to a console, which shows you the activities that you'll perform. And then this is what is called the file explorer view, which is the one that will open by default. You'll see this file at the extreme left menu. There are two more views. One is the compiler view. You can select this. This is a second in line. And then finally, you have deploy and run transaction view, which will help you run transactions after you've deployed the contract. Now, when you run Remix for the first time, it will automatically create some contracts for you, some Solidity contracts. And these are some contracts that are very, very good for some basic, testing and familiarization process for the end-to-end flow. So take a look at this first contract, which says Solidity, storage. If you double click, it will open this file in this right box, and it will basically show you the code. Before we jump to the code, the first thing that you have to see is that this is a file with an extension .sol, which means Solidity. Now, once you have this contract available here and ready to, analyze and test, what you have to do is first decide on the level of compiler or the version of the compiler that you want to use. So Solidity normally operates in a compile and deploy mode. Not really normally, it always operates that way. So when you talk about JavaScript, when we talk about TypeScript or VB script, shell script, all of these scripts, they don't compile. The process for them to be executed is through a process of interpretation, where You just execute them, and there is an environment that interprets all the commands and then runs them one by one. For those of us who are familiar with C, C++, Java, or some of the later languages like Rust or Golang, they understand that that is not how it normally works. You have to first convert your source code into compiled format. That compiled format is low-level instruction set that your environment will understand. So having said that, you'll have to give me a very short water break. I'll be back in about 2 minutes and then we'll resume this. Apologies about that.
Just wait for a second. Our host will rejoin with us soon.
Hi, sorry, I'm back. Apologies. All right, so coming back to what we were discussing, Solidity is a language that basically gets compiled into what is called bytecode, or an assembly instruction set that is understood by the Ethereum virtual environment, or EVM. So this environment is going to do that for us. It's going to compile this source code. It will convert it into bytecode, and then it will help us test that bytecode also. Now, before we move any further, let's do a quick analysis of this code, because it's very simplistic and it will not take a lot to understand what it is. The first thing that we have here is the compiler version that you want to use. So we have these keywords, pragma. Pragma is a directive that C++ folks will understand very well, but it basically informs the compiler that the features that we're using are between versions 7 and 9. Next is contract keyword, which basically indicates that we are going to be writing a smart contract. This is the name of the contract. And then whatever is inside this curly braces, that's going to be the logic of the contract. Now recall that we said that Solidity is a Turing complete language, which means it gives all the features of a regular programming language. Here we are just looking at some basic, very basic, in fact, trivial features. So what we are doing is, first we are declaring a field. This field is called number, and its type is unsigned integer of the length 256 bytes. So this can be a number which can have a minimum value of 0 because it's unsigned, and a maximum value of 2 to the power 256. So it can be very big. Then we are implementing two functions. Functions are like routines or methods depending on which language you are in. One is a store function, which basically accepts a number as parameter and then assigns it to this field. So you can think of it as a setter also. And it is declared of the type public. Next, we have a retrieve function, which is also public, which declares that it will return unsigned integer 256, and it returns this field value number. The one thing that you will notice is that this also has a modifier view. View means that this function is not updating anything. It's just reading or it's viewing something. So there is an implication in Ethereum of a function being a view versus not view, which we'll talk about. So we basically looked at a very simple smart contract to start with. Now the question is, how do we test it? How do we run it? So Remix provides all the facilities to do that. You have to first go to the compiler view. In this compiler view, on the top, you will see the version of compiler that we will be using. So you could select any one of them. For the purpose of this contract, it doesn't matter which version you're using. Then Remix also supports Yule, which is another EVM compatible language, but we'll not be looking at Yule contracts yet. Then it also allows us to select the EVM version. Now the EVM itself, the environment in which this contract runs, that has also been upgraded over time. The latest one is London. London is a EVM upgrade we had in, I think, December last year. So these are all sequenced chronologically. Feel free to select anyone if there is a need. Otherwise, you can select compiler, which is by default selected. Then there are some flags, auto compile. You can select auto compile. What that will do is every time you change something here, it will quickly recompile it. So you don't have to keep pressing this compile button. Now, as I selected auto compile, it automatically compiled the contract here and it created this section. This section has the compiled code. If you had more than one smart contracts, this drop down will have all of them. You can publish this to IPFS. Not really something we'll go into in this session. And then there are some compilation details. If you click this, you'll see some details about this contract, like its name is storage, and some metadata about it, like which compiler, what language, and a bunch of other stuff. The important stuff, or the important part of it, is these two, the bytecode, which is the compiled output. This is the bytecode. More specifically, this object. This is the output of the Solidity compilation. And what gets deployed on the blockchain is this. And the second thing that's important is the ABI. ABI is a JSON object that is the description of the contract functions and interfaces. So if you expand it, you'll see that there are two elements in the ABI. One is the function retrieve and some description about it, like it's a type function and it's a view function type and it returns unsigned integer 256. The second is the store function. Some description about the store function, as in its parameter is unsigned integer 256, and it is a type function. So this ABI is basically the definition of the smart contract without the logic in a pre-structured format. If you copy this ABI from here, and let's say you want to see what it is, you can paste it on a text editor and you'll see this JSON object. So I'm hoping we are familiar with JSON. It's an object description format for JavaScript. So coming back to our contract, we've basically successfully compiled it. Then let's go to the deploy and run section, which is right below compilation. Now this is an important section because this is where we'll actually see the execution happen. Before we get in depth on what these different sections mean, what we have to understand is that the blockchain that we have to deploy this contract to, that is the main production blockchain, it is not installed on this machine or is not there as a distributed ledger on this machine. So to be able to test it, we'll have to deploy this contract through another machine that basically is a legitimate node on the blockchain. Because to deploy this contract, we'll have to send a transaction to the blockchain, which can only be sent through that node. Now, since that is a very difficult, not really a difficult, but that is a slightly complicated process. So what Remix has done is that it has built a very, very minimal blockchain inside this Remix environment itself. That is the one that you see on the top, which says environment. Now this JavaScript VM, this is a blockchain that is inside the Remix environment itself, ready for us to use. If you drop it down, you'll see some other options like injected Web3. What injected Web3 will help us do is connect with MetaMask, but we'll try to see how that is done after some time. And then Web3 provider. Web3 provider is a direct connection to a node using its IP address. We'll see how that is done also. But before doing that, we'll first try the easy thing. We'll just use Remix's blockchain because that integration is very, very, very easy to observe. The next thing is the accounts. So you'll see 10 accounts that are already created here. What Remix does is that if you choose to use Remix's environment, which is this JavaScript environment, then it automatically creates 10 accounts for us for testing, each one of them with some basic funds like 100 Ether here. So what this will do is it will give us a set of ready accounts that we can use for deploying contracts, calling contracts, because every time we make a transaction, we have to spend some money. That money is already added here. Now remember that this is a local blockchain. It's not even local, it's inside memory of the browser. So all of this is actually not real money. When we look at 100 Ethers, it's just created as stored value on the blockchain against an account and just given to us for testing purposes only. The same concept we will see in our test nets as well, when we will be deploying on testnet. A part of testnet was what we saw earlier yesterday when I transferred some Ether from my account to another account. That was also done on testnet. Then gas limit, this is the amount of gas units I'm willing to spend. Value is if I want to send some extra money, which basically is used for either executing some part of financial transaction inside the contract or investments or staking purposes, which are a part of our, which could be a part of our logic if we choose to implement it. So this is the compiled contract, and there's a red orange button below it which says deploy. So all I have to do to deploy is just press this button and it will deploy it to the local Ethereum instance. So I just click it. There is a transaction that gets created here. You can see this transaction in detail. It looks very much like the transaction we saw on the Ethereum blockchain on Etherscan. So you got the transaction hash, you got the from, you got the to, gas, and so on. But this transaction is actually a transaction that we executed as a part of deployment of the code. So what this transaction did was, if you look at this input was that same bytecode that we saw during our compilation process. So once this deployment is successful, you will see this entry here right below, which is going to tell you that the contract is deployed. It's deployed at this address and it's in memory, which is why it's saying memory. If I expand this a bit, you can see memory, which basically indicates that it's an in-memory blockchain. And then you see the two functions that we have implemented, store and retrieve. Store is a function which is kind of shown in the red because it's updating the state of the blockchain. Not really the state, but the contract state, which rolls up to the state of the blockchain. And the other is retrieve. It is in blue because it's a view function that doesn't update anything. When I will execute this store function, I have to pay a small transaction fees. The reason for that is because my transaction needs to be executed to update the blockchain itself. But I will not have to pay any fee for retrieve because I'm just viewing the state of the blockchain. I'm not making any updates. So what first we should do is let's just check the value that this number has using the retrieve call. So when I call retrieve, I'll get this value as 0 because Solidity initializes all its parameters, which are numbers, as zeros. So you'll see 0. Now let's update this number to some random integer. Now when I will call store, this is the store execution. What will happen is the transaction fee will reduce my balance. You can see the balance came down from 100 to 99 point something because I ended up paying some transaction fees. This balance also was reduced when I deployed the contract because that also was a fee transaction. And every time I'll call store, you'll see that this balance keeps going down. You can actually see it right now. So now this value has been stored. Let's try to retrieve the value. And as you can see, that the value is now what I had set it. So basically analyzed, compiled, deployed, and tested a smart contract. Now there are two more steps. One, I would be deploying this contract on the testnet. When I say testnet, it will be a network that will be visible using Etherscan because it's remote. It's a real blockchain. And then I will be using MetaMask to deploy it, because when I will select testnet, I will have to hook up my MetaMask to that testnet, and then Remix will use my MetaMask to connect to that testnet. And these accounts are not going to be visible here. The only accounts that will be seen are the ones that MetaMask has configured for me. Now, since my machine had crashed yesterday, so I don't have MetaMask initialized yet. I installed it today morning, but it's empty. It doesn't have any accounts. It doesn't have any configuration. So I'll have to start the process again. So when I click get started, I can either create a wallet or import a wallet. Now I already have a wallet with what is called a mnemonic that I had created for my testnet. So this is the mnemonic for that wallet. Copy it. And I can just paste it here. And I can set up a password. Now I have not imported any accounts. Let me import my testnet account just like I did yesterday. And I connect to and I connect to the Kovan network. In this network, this account has good amount of funds so that I can do all my deployment and testing and everything. Now, once I have set up my MetaMask, what I need to do is select Web3 provider, sorry, injected Web3, which is, so Web3 is basically a concept that is proposed by blockchains, which says that all applications should be on the blockchain. It's talking about a decentralized web. So you'll see this term being executed or being mentioned at various locations. It just means that we're talking about blockchains. So once I select Web3, you'll see that it launches MetaMask automatically, and it selects the account that has some money. Once I click next and connect, it's going to connect that account and bring that account here. So now I don't have those 10 pre-funded accounts. I have the network, which is Kovan selected here, and a single account. Now what I can do is the same process, nothing else changes. I click on deploy, but this time it's going to launch MetaMask. And it's going to ask me to confirm the deployment because I have to pay some gas fees. So I confirm it. It's going to take some time to deploy. I can view this deployment on Etherscan. Now Etherscan, with its slow databases, takes some time for the transaction to appear. So this deployment transaction hasn't appeared yet. I'll have to constantly keep refreshing to wait for the transaction to appear before I can start interacting with it. This is that, no, it's 1 day old. So in Remix, you can see this transaction has been confirmed, which means it's on the blockchain. In fact, it's created an instance of the transaction here, so I can check, I can test this transaction. One thing to notice is now it's no longer same memory because it's deployed it on a real blockchain. I can send transactions for retrieve, which gives me 0. I can send a transaction to update. Now, obviously, update requires me to send to pay a transaction fees. Which I do. Let's see if it is now appearing on Etherscan. It's not. But anyway, I can check that my update is reflecting here because my transaction was confirmed as MetaMask told me. All right, so we'll give it some more time before we'll come back here to view the transactions. So any questions on what we've done till now? We have about 20 more minutes. We will take a look at some other tools that help us use our local test environment, specifically a tool called Ganache, which is used by most of the developers on Ethereum blockchain, especially smart contract developers. So before I start doing that, any questions, thoughts, comments? All right, in that case, the other tool that, so this is Remix. We've seen most of the functionalities that Remix provides. It also has some other more complicated contracts which use some other features of Solidity. We'll try to see a detailed Solidity contract, but before that, let's try to learn about the tools and capabilities of the Ethereum development environment a bit more. So we have seen Remix's internal blockchain, which is a very good tool for internal testing. We've seen this testnet environment, which again is a very interesting, not really interesting, but a good way to test smart contracts because it operates exactly like it would on a real blockchain. So now the transaction has started appearing. This was a transaction I made 5 minutes ago, which was the contract deployment transaction. So you can look at this contract. This was a contract we deployed. You can see the contract decompiled format. We deployed the storage contract. It's even got the comments and the function names and function comments correctly. This is the contract ABI. And we also made a transaction on this contract, which was, first one was the contract creation transaction, which was basically the deploy transaction. The second one was the store call. So if you want to look at the store transaction, you can see here, this was the transaction. It was made 3 minutes ago. And in this transaction, we called the function store and we passed some value to it. Now, coming back to Remix, there's one more option that Remix provides for deployment purposes, which is, so we've seen injected Web3, which is basically MetaMask integration. Most of the times, if you build on Ethereum, you will be doing this. The other is Web3 provider. Web3 provider expects you to provide the IP address and port number on which your node is running. Now, what that means is that if you set up your own node, then you can submit transactions to that node from Remix using this facility. Now, one thing that you have to remember with Remix is that it is available only over HTTPS, which is why you will not be able to access an HTTP URL because Remix is on HTTPS. However, what you can do is if you load Remix itself with HTTP, I don't think it allows you to do that. It's still going in HTTPS. Let's see. So to be able to use it, what I have to do is set up my own blockchain node. Not in memory, not through MetaMask, maybe through MetaMask. MetaMask can also connect to that node, but I have to basically set up a node. So an easy way to do that is to use a tool called Ganache. So for us, there is a very easy, for us, by us, I mean Linux users, there is an app image of this tool available for download that one can use for basically setting up that blockchain. You'll have to give me just one moment. I'll be right back. Sorry about that minor interruption. So coming back to Ganache. So you can, if you're using Linux, you can download this image from, and you can basically Google and when you go to the Linux download section, it basically downloads this app image for you. For Windows, I think there is an install and an executable, but I've not used it. So once this is downloaded, you can just launch it from the terminal. And it launches a UI for you. And in here, you can very quickly start the Ethereum blockchain by just clicking on Quick Start. And it does something very similar to what Remix was doing. It creates a set of accounts that are all given 100 ethers each. And it can show you all the blocks and the transactions that you're going to be submitting. Now it's RPC interface, which is the interface used for connecting to Ethereum node, is here. So what you can do is you can just copy it. And since we are developing in Remix, we go back to Remix, select Web3 provider, and enter this URL. Now this problem that we're looking at, that it's not possible to connect to Web3 provider, is because of the HTTP and HTTPS issue. Now this is more of a Chrome issue, that it always redirects you to HTTPS. So what I can do is I can launch another browser, Firefox, and I can launch Remix from here. Now Firefox doesn't complain if I start using HTTP, which means when I go here, before which I'll have to just compile the contract. Now if I go here and I select Web3 provider, or maybe just paste it, and it connects without any problem. You can see that it's connected to this network. It's imported all the accounts that are there on my on Ganache network, on the Ganache blockchain. And I can operate from here just like I was operating on, the local blockchain. To do that, I can simply test my deploy function. I can see that there is a deploy transaction created here. If I expand it, I can see all the details of this. This is the bytecode that I deployed. And then I can test the function calls. Like I can see another, I should be able to see another transaction, this one. First one was the contract deployment. Second one was a contract call, in which this was the data I sent. This is obviously encoded data. I can make more transactions. All of these transactions are going to appear here. So it's operating like a regular blockchain. Usually creates one block per transaction. You can look at the block as well. So, and some of the other details that you can do is you can take a look at the logs of the blockchain. So these logs are basically low level outputs that get created when you start operating on the blockchain. With C mining, status is auto mining, so every transaction will automatically be confirmed. There is a gas limit and a gas price, all of which you can change as needed, like from here. Change the hard fork number to the latest one, supporting these many at this point. And then it also gives you, oops, I think I stopped it. So it also gives you a way to look at the private key of each account. This is the private key. This is a private key. What that helps you do is, if you want to send transactions from a UI where you want to enter the private key on your own and not use MetaMask, then you can use the private key that you copy from here and then just basically use it in your UI. Now we've done three things. We've created a local blockchain through Ganache. We've created a testnet contract deployment through testnet integration with MetaMask. And we tested that same contract locally inside Remix. Now, what we basically are left to do is to create a client for that contract. As in, you don't expect, let's say if you build a decentralized application, you don't expect the user to be entering, values from here. User would either expect a mobile application or a browser application, which probably will present a form in which they will enter their details, and that should go to the blockchain. To do that, we have to understand a capability called Web3j or Web3js or Ethers.js, which allows you to basically sign transactions and then send them to the blockchain. It allows you also to integrate with MetaMask, just like Remix is integrating, and send transactions using MetaMask signing to the blockchain. So we are towards the end of our session. That client development is something that we will do in the next session, along with creating your own blockchain through. So this Ganache tool was just a tool. It doesn't really tell you what kind of blockchain you're creating, and it's not good for production. So there's a way in which you can initiate your own blockchain, like your own private blockchain. And for that, you'll need a tool called Golang implementation or Geth. So we will be doing two things tomorrow. One is we will be setting up that local blockchain using Geth. And two, we will be creating a client application, a simple browser application that's going to use MetaMask to send transactions to the storage contract. And we will, at a very high level, also try to understand what are the capabilities of Solidity. We've only seen Solidity at a very high level. So that's the part that we will look at for Ethereum. The next part that we'll take a look at would be for Hyperledger, where first we will analyze Hyperledger a little deeper, and then we will deploy a business network, a sample business network that Hyperledger provides, for which we will understand Docker. The good thing is that my machine is fresh, so I'll have to do all those steps from scratch, which you can actually see and do or replicate on your own. So having said that, we kept good time. Today we were able to cover a lot. Again, I would request you to be forthcoming when it comes to questions. I usually keep half an hour for questions and I still run out of time, which is why, we are able to keep this good time, but that isn't really what I would prefer. If there was a lot of questions and engagement, it would make the sessions more fruitful. So we have 2 minutes, leaving the floor open again for any questions.
Participants can ask question to the sir. Okay, sir. So we will wrap today's session here.
Okay.
Okay.
Feel free to try out some of these things, and if you run into
Sure.
any issues or questions, we can pick
Surely,
those
sir.
up tomorrow. Yeah.
Surely, sir. Thank you very much, sir, for
Thank you.
sharing us
Thank you so
the
much.
practical session with us through the last session.
Sure. Thank you.
Sir, there will be one question from Hani Gurnani.
Okay. Try out. We will try out and then let you know of any doubt. Okay. Yeah. Sure. So not really a question.
Yes, sir.
Basically saying that they'll try it.
Sure.
All
Okay,
right.
sir.
Thank you all. Thanks for joining.
So thank you. So we will wrap our session over here. Tomorrow we will meet at 10 a.m. See you soon. Have a great day.